Hi everyone. In the last class, we are seeing the advanced networking topics, and there are different things which we have seen. If I have to revise it, uh, yes, we have seen about multiple nodes and multiple interfaces, how they are communicating, and we have seen like this is a config file where hyphen node IP is mentioned to by the kubelet specifically, and we have seen that for network troubleshooting what all we can do, like we can verify where we can verify the CNI plugins and IP forward command. We have seen how to set it, and we have seen different analogies also to understand it clearly, and we have seen that there is one module called BRNet filter, which is basically very important for translating and for services or ports communication to not drop the packets, or to avoid the waiting for connection. So this BRNet filter, where the translation happens from layer 2 to layer 3, it goes to iptables, and basically the service IP, which is virtual IP, to the real pod IP is how the request will forward that responsibility. Without this BRNet filter, that will not happen. So there is a way that we can basically do it. If it is not there, that is using mod prob BRNet filter, and yeah, we can verify it using ls mod grep BRNet filter. If it is not there, we can fix it using this command. And we have also seen to debug the pod to pod connectivity, exec into one pod and then ping the another pod. If that another pod is not responding, something is failing in, and you can just check the routing tables using ip route command, and you should be able to see that pods CIDR. If it is not there, something is wrong with that translation. And we have also seen the host network. If it is true, what happens? If it is false, what happens? And how the security implications. And we have also seen about yeah, I think that's it. So yeah, coming back to section number 3, overlay networks versus direct routing. There are ways to basically enable the routing, and CNI is responsible for IPs, connections, routings, and all, right? So there are certain CNI plugins which uses overlay method, and some CNIs uses the direct routing. Overlay is nothing but, if you see here, the pod 1 IP address is encapsulated inside a node 2 IP address. So this pod IP address, let's say this pod has to communicate to this pod. So directly IP to IP is not translating. First it is encapsulated inside the node 2's IP address. Then the request is going into node 1's IP address, inside which the pod 1 is there. So encapsulation is happening. That is communication using overlay networks, and it is like overhead to the CPU. Another way, alternative scenario is where using a direct routing, it uses certain protocol like BGP and different methods or other protocols, but generally it's a BGP that is used by Calico. It's like direct routing. If pod 1 has to communicate to pod 2 with the direct IPs, it can communicate. This is less overhead to CPU, but it has different other cons as well, like it has to exactly know where the node exists and its pods area, all these things it has to do. So it's extra work is there, like that. And coming to the section 4, it's about services internals. So I think it's a bit deep. So if you go to the kube-proxy, basically a kube-proxy, I told that we already discussed it previously many times, that whenever a service is there, a pod is going, the pod's request is going to the service. The service will be having a virtual IP address, let's say. This virtual IP address, when BRNet filter module is enabled, that IP will be translated to node, that IP will be translated to that particular pod IP address. That translation basically happens through kube-proxy. And this, how does it do? It just does like a rule manager. So whenever a service is created, this kube-proxy is acting like a daemon set. Okay, daemon set means it's up in all the nodes. So when something is happening, like some service is created in one node, kube-proxy of the other nodes also will write into the Linux kernel the IP tables. Like, okay, if the request goes to this particular service, that means the request has to be translated to this particular node CNI bridge or something like that. IP translations it will write into the Linux kernel. So like that, if it has to maintain all the rules of all the services, it's an overhead, right? So in order to so some kind of advancement in IP tables is like IPVS, IP virtual server, and another kind of advancement we have is eBPF. So this is like extra knowledge, but yeah, basically this is what kube-proxy is doing. And now there is one more thing called destination network address translation. So let's say a pod A is sending a packet to the virtual IP of the service. Here mostly in the section we are focusing on services kube-proxy only, so bear with me. And now whenever a pod A is sending a packet to the service VIP, okay, and the packet hits the node kernel. Since the kernel is having the address translations, it will be catching that rule in the IP table, and the kernel basically sees that, and because IP tables have mentioned the translations, it will translate that IP to the real destination of the IP address. And the kernel writes a note in its memory, like as I changed the pod A's request from virtual IP to the pod C, the pod C replies, then you have to reply back to pod A. That reverse, if let's say pod A, I am basically communicating to the service virtual IP. I don't know about the pod existence, but the kernel knows. If it comes to this IP, I should be translating to this particular pod based on the labels and all. Okay, so but when a pod responding from here to where it should go, the request, that reverse request, response also, it will be catching that IP address of pod A, so that it can translate or send that response to pod A from the pod B using contract. So that happens. This is reverse translation, and this is by using the contract memory, and changes the sender packet, sender IP from this particular pod IP to the service IP again, and it will send back. And there is some alternate scenario also you can see. Okay, and yeah, there is one more section 5. This is my favorite, I think, because it has cleared so much of noise inside my head on the service and DNS. So let's actually read it. To truly understand the cluster DNS IP, 10th IP, and etc resolve conf, we are going to track exact step-by-step journey of a single request. Okay, now, so basically, if you remember, I told you that when a pod is created, each pod will have a location as etc resolve conf, and in this location we will be having an IP of DNS, right? And that will be the 10th IP address of the service CIDR range. and this will be a virtual IP, right? That service CIDR is a virtual IP. So how basically the DNS IP is involving here? Let's see. Let's say like a front-end application says I need to send a GET request to a particular database called my database. But networks only understand IP addresses, not words. But my front-end application says I need to send to this particular database. So the app asks Linux OS inside the container for help. Now inside the container, that means inside the pod, inside the container, there is a location called etc resolve conf. It checks that configuration file, and when a kubelet originally built this pod, it forcefully injected two crucial things into this file. One is this thing, search default conf service cluster dot local. So this is like if app asks for a short name, append this domain to it. So my database instantly becomes my database dot default svc dot cluster dot local. Basically this is written commonly in that etc conf file, and it says that if any ask for a short name, you have to append this thing. Okay, it has appended. Now what? So to find the IP address for this long name, send the DNS query to exactly this. This is the 10th IP of the service CIDR range. And you remember this, service CIDR range is a pool of virtual IPs. Out of this, first to 10th IP address is assigned to the DNS. So basically it's like whenever a request is coming, that is appended to this particular domain. So service name, also something like default is like a namespace. Okay, my database name. So is a name of that resource. Default is a namespace and cluster.local is appended. And in order to find the IP address of this, you have to communicate to someone. It's like a head of a colony or something like that. That's a DNS IP. And you know, if you go to actually kube system namespace and get the pods, you will see one pod called core DNS pod. So this is actual pod, and we know that pods will have an actual IP address, right? But here, whatever the 10th IP address, this is a virtual IP address. It's not a physical IP address. So whenever the packet tries to leave the node, kube-proxy iptables translate it. Now again, kube-proxy is responsible for translation to the exact pod whom you are referring to. Maybe basically the labels which are there in this particular service, who is having a IP address of this is referring to core DNS pod which is running in kube system namespace. And let's say this IP address of the pod is this. So it will translate from, and I hope you are clear, right? So basically what I'm trying to solve here is how does the connection to DNS is there. Okay, and so every pod, inside every pod container, if you go here, whenever a pod is created, your kubelet injects something into this file. That something is a DNS. And how does that help? The DNS will have a virtual IP, but actual is a core DNS. It is running like a pod, so it will have a actual IP address. So your virtual IP to actual IP translation happens via kube-proxy. And now what happens? The core DNS pod is looking into it and checks what is the IP from my database dot default dot service dot cluster dot local. It is constantly watching the Kubernetes API. It checks its internal memory and replies, this is the IP address from my database service called this. So the involvement of DNS, it's like, who is basically doing all this? First, the request goes to DNS only. Okay, and DNS translation happens via kube-proxy. Now the real thing which is doing by core DNS, it checks its book and says that this whatever you're checking, okay, database, something like this name is belonging to this IP address. So I think the request has to send to this IP address. Now what happens? The DNS lookup is complete and the front-end app receives the request. Okay, now I should send to this one. Now the app generates the actual HTTP GET request packet and address to this. But leave it. Wait a minute. This is also not the real IP, because according to its memory, this is one database service IP, and we know that services will never have a real IP address. So again, this will be translated to a real IP database of the which is having the real IP. So that virtual IP gets translated to a real pod's IP address. So yeah, if you're looking for a database virtual IP, let me translate the destination to a real IP of the database pod, which is this. So exactly then the physical database pod gets the request, and of course there will be some contract, which is connection tracking memory, where it is getting from the request. So it will send exactly the response to the particular front end pod. So yeah, the 10th IP is nothing more than the permanently stable virtual friend node to the core DNS phone book. It is injected at every pod nodes exactly where to ask for directions. If that pod doesn't exist, pods would have no way to find the ephemeral IPs of other applications in the cluster. So yes, that's how it happens. See, there is so if you want me to explain via diagram, what happens is, this is a pod. First, the pod request, actually there is a DNS, okay, and DNS first, there is a core DNS also, which is an actual pod, and there is a service for this, and this DNS service basically is having a virtual IP address. Every node, if you have node 1, node 2, node 3, node 4, any node, all these nodes, wherever the pod is created, all those pods will be injected with etc resolve conf file, which is having the IP address, same IP address, 10th IP of service CIDR range, same IP address will be there. because service CIDR is a global IP addresses, right? Global virtual IP addresses. Out of this global that means globally it is a global range, and out of this 10th IP address, so this 10th IP address will be present in the pod's location. Pod just doesn't ask for the IP address of the service. It doesn't know. So actual translation happens from the pod to the core DNS via the DNS service. But in the middle, from DNS service to pod, translation happens via kube-proxy. And yeah, it reached, and it then gives the response to the pod like via the service only, of course. Like whatever you are searching for, that name translation it will do to the IP address. Since it's a service IP, it will give that virtual IP of that service. Again, the pod only has to take that, and the kube-proxy has to translate it, and it will translate to the real pod IP, and it will basically navigate that request to that pod IP, and this response will come through this VIP only to the particular pod which is requested. Let's say this is front end and this is back database. So that is how the DNS is involving. That's what my doubt is, like why DNS is involved when the IP's services happily the kube-proxy is translating. So why? Then I understood a bigger picture now, that DNS is responsible for giving that exact service location. This is just kube-proxy is just like an agent, it's writing, of course it's writing the rules, it's doing a very important task inside the kernel, but actually this is one of the subtask of the entire translation that is happening, entire request and responses that is happening. I hope it is clear for you, and I know it's a bit confusing and a very big topic. Yeah, thank you so much, and have a good day. Bye bye.